here we are. Spider-Man No Way Home is out, and no piece of Spider-Man media could possibly top it. So why do I even bother? One of my favorite parts of the movie was seeing Alfred Molina as Dr. Octopus again. 17 years later, and Molina still plays the character beautifully. And of course, once again, we see the arms. It's been a film effect that's mesmerized me my entire life. These tentacles, they have this way of sticking in your mind, as if you've witnessed some higher life form. Artificial, yet extremely advanced, able to take control of a brilliant scientist's mind. Artificial intelligence, by the way, is a field that has progressed at an insanely exponential rate since 2004, when Otto first mentions the concept having to do with the arms. We have artificial intelligence behind all sorts of robots. Check out this robot, for instance. It's learned on its own how to catch things. This robot has learned how to tie knots. This is not really a far cry from the behavior we see from Doc Ock's tentacles in both Spider-Man 2 and Spider-Man No Way Home. But these real-life intelligent arms are not tentacles. That's a huge part of the appeal of Doc Ock. I mean, could you imagine if he just had 4 7-axis manipulators coming out of his back? It'd be a completely different vibe. Not as elegant. It's like if Doc Ock was the manager of a Ford plant or something. That's why for me, the mechanism of a tentacle has always been the most interesting aspect of Doc Ock. Here's Otto Octavius, a world-renowned physicist, and he decides, I'm going to mount 4 squiggly bits to my back to help me with nuclear fusion. I mean, this is a guy with style, if nothing else.
Very well.
The way the effects guys designed the tentacles in Spider-Man 2 was really brilliant. They look as if they could function in the real world, with a mechanism pretty much anyone can pick up on just by looking at it. You have a manipulator consisting of many segments, called links, connected by joints. This is standard language when talking about mechanisms. These links are constrained by 3 cables, whose pulling cause 1 or 2 of the 3 sides of the tentacle to shorten, so that the tentacle is forced to bend in the direction of the pulled cables. In this way, the links can be thought of as bones and the cables can be thought of as muscles. Seems simple enough, right? Let's do a thought experiment and simulate the results with all the necessary physics. Let's say in 2-dimensional space, we have a tentacle with 8 links. Gravity acts on this tentacle, causing downward acceleration. This tentacle is not stiff. You can assume all the joints are simple pivot joints, with no returning force to any stable equilibrium. There is friction in the tentacle joints, so energy can be dissipated. The tentacle is mounted horizontally, the same way it would be on Otto's back. We start with the tentacle at rest in a perfectly straight configuration, outstretched with all joint angles 0. What happens when we let the tentacle drop? You predict it. Will it A, fall, or B, remain outstretched? If you said fall, you'd be correct. Gravity acts on all the links in the tentacle, causing it to fall down so that all the joints are as low as possible. This is pretty easy to grasp. Now let's add a muscle along the top of the tentacle, running through all the links and attached at the end of the tentacle. Say we start with the tentacle again outstretched horizontally, and we constrain the cable between the base link and the last link. This is a constraint that basically says the distance of cable between these links is not allowed to change. We are effectively holding the cable in place once the tentacle is outstretched. What happens when we let this tentacle go? Predict again. Will it A, fall, or B, remain outstretched, or C, rise further? If you said remain outstretched, you'd be wrong. The tentacle still falls. The end curves upward and the base curves downward, allowing the cable to remain the same length. This cable configuration cannot fully constrain this system. What happens if we then start to pull on this cable, further shortening the top side of the tentacle? Could the tentacle become horizontal now? Nope, just rolls up. This behavior makes the arm utterly useless as a robotic manipulator. I mean, if you can't reach outward, what good is your arm? This is all because of the nature of a tentacle built like this. It is what we call an underactuated system. What does this mean? Take a look at this 2D tentacle model again. How many joints does it have? 1, 2, 3, 4, 5, 6, 7, 8. Tons of joints. And what does that tell us about how this tentacle could move? Any of these joints can move independently, right? That means we need 8 numbers, 8 joint angles to fully define the position of the tentacle. We call this 8 the number of degrees of freedom, DOF. For instance, our human arms have 7 degrees of freedom. Our shoulder has yaw and pitch, 2 degrees of freedom. Our upper arm has axial rotation or roll, 1 degree of freedom. Our elbow can bend in one direction, 1 degree of freedom. Our forearm has roll as well, 1 degree of freedom. And our wrist has yaw and pitch, 2 degrees of freedom. We are also able to fully actuate or move throughout these degrees of freedom independently, meaning we have a perfectly actuated system, not over or underactuated. It's fascinating that we have 7 degrees of freedom because most human-engineered robotic manipulator arms also have 7 degrees of freedom. This isn't just so that they're similar to humans, but rather that humans evolved to have 7 degrees of freedom in their arms for the same reason that engineers create arms with 7 degrees of freedom today. The reason is this. In order to align an object as desired in space, it has to reach a desired position, which is X, Y, and Z, and a desired orientation, roll, pitch, and yaw, which are the angles it must be rotated about the X, Y, and Z axes. This means 6 degrees of freedom are required to hold an object in any position or orientation in our 3-dimensional space. These 6 numbers together are called the configuration. The 7th degree of freedom is called redundant. It gives the arm more options for the path it can take from one configuration to another. It makes path finding easier. Let's get back to our tentacle. I said it was underactuated. That means that while we have 8 degrees of freedom in the mechanism, each one is not actuated independently. We don't have 8 little motors in this arm. We have a single cable muscle trying to shorten one side of the tentacle, a single actuator. And the fact is, with the top of a tentacle constrained to be a certain length by this muscle, there are an infinite number of configurations that satisfy this requirement. So who decides which configuration the tentacle ends up in? Well, gravity. Gravity decides. So you see that the mechanism is not as simple as we first thought. Obviously, our desired behavior for this tentacle is to have our muscle precisely coupled to a single degree of freedom in the form of a bend angle. That way we can match however many muscles we have to however many bend angles we have and have a perfectly actuated system. The many degrees of freedom must be coupled into a fewer quantity. A single cable must move several of the joint angles simultaneously. I'm going to show 2 ways to couple the joint angles. To recap, determining whether a system is under or overactuated depends on the number of degrees of freedom compared with the number of actuators. If there are more degrees of freedom than actuators, you have an underactuated system. If there are less degrees of freedom than actuators, you have an overactuated system. So to deal with all of these degrees of freedom, we need more actuators, more devices that can transmit force, while not adding any more motors to pull on the muscle. One way of doing this is by increasing the stiffness of the joints. Obviously, the extreme version of this is simply mounting a completely rigid version of the tentacle horizontally and saying, hey, it can stretch outward. What's going on here, of course, is that the gravitational force on each link is not sufficient to cause it to bend. Because the tentacle is rigid, its joints have an extremely high stiffness. However, no actual cable, muscle, and motor would be able to bend this tentacle, well, because it's rigid. We saw before with no stiffness that the tentacle just drops to the ground. So we need somewhere in between, where the stiffness of the joints can help exert a force that counters gravity, and will also distribute the cable's tension force effects throughout the entire tentacle, but not so stiff that any bending becomes unfeasible. So as you can imagine, there's a lot of room between 0 stiffness and essentially infinite stiffness for us to play around in. Going back to our simulation, watch what happens when we increase the torsional stiffness of the joints from 0 Newton meters per radian to 0.5 Newton meters per radian, to 1 Newton meter per radian, and finally 2 Newton meters per radian. As the stiffness increases, the neutral top cable length constrains the tentacle to a more and more horizontal position. As the cable is pulled, the tentacle bends more uniformly instead of just rolling up at the end as before. With this simulation, we can directly probe the tension in the rope and see how it changes with respect to the angular position. At the maximum bend of this simulation, 4 radians or about 230 degrees, the tension in the cable muscle reaches about 18 newtons, or about 4 pounds of force. That's a lot. It'll be hard to find a motor to winch that up at any useful speed, and this high tension comes from the counteracting of the stiffness. So while this is an easy way to increase the controllability of the tentacle, to more precisely control the end effector position, it comes at the cost of controller effort. This problem of controller accuracy versus controller effort is a super common one in the field of controls, and is the source of many optimization solutions that help design controllers. One other more complex way to couple the degrees of freedom is by coupling them using rigid body mechanisms, rather than applying deformable stiffness between joints. Let me ask you a question. Let's say you have a tentacle mounted horizontally and you want all the joints to bend an angle that corresponds to the shortening distance between the tops of the adjacent links from L to L prime. The difference between which is delta L, so giving 4 moving links, the entire length of the top of the tentacle changes from 4L to 4L prime. So a cable that stretches the entire length of the top of the tentacle must be pulled a distance 4 delta L. We should know by now that this cannot cause all the joints to bend the same way, but let's now say, to add some correction, we can add a cable attached to the third link, running 3/4 of the length of the tentacle. For this cable to match the desired bending, it must be pulled a distance 3 delta L. We can continue this pattern, 2 delta L for a cable attached to the second link, and 1 delta L for a cable attached to the first link. We now have 4 muscles that must be pulled different distances. But these distances are related by a simple formula. The nth cable must be pulled a distance equal to n times delta L. This can be accomplished with a single motor driving n pulleys of sizes ranging from a radius r to n times r. When the motor rotates an angle theta, the distance that each pulley will pull will range from r times theta to n times r times theta, i.e. r theta, 2r theta, and so on, actuating every single degree of freedom in the tentacle simultaneously and as desired so that all the joints bend the same amount, culminating in an overall bend angle for the tentacle. Now this of course has its issues, as all solutions do. This can be accomplished without any stiffness in the tentacle joints, so the motor will no longer be resisting that returning force, but these coupled pulleys and several cables will add a lot of hardware to the design, which is not ideal if you're going to mount this on a harness, as I intend to do one day. Maybe there's a way to combine the solutions, have some stiffness, but not enough such that the tentacle can be outstretched using a single cable, and multiple cables, but not actuating every single joint. Let's take a look at this tentacle, which I am attempting to operate in 2D by just showing the effect of actuating the top of the tentacle. This 8-link, 8-joint tentacle has some stiffness. It can't completely collapse when under the influence of gravity, but it gets close, and we can see the shape that it takes is eerily similar to my simulation. It seems like I did something right there. When actuating a single cable muscle attached to the 8th link, we can see the end rolls up while the base doesn't actuate much. This again is exactly what the simulation did when provided with minimal stiffness. We can see, however, that with just a bit of help at the center of the tentacle, the last 4 links can be constrained to be horizontal just fine by the single cable. So let's just attach our next cable at the 4th link to help the base half of the tentacle out. We can already see a big difference with just 2 muscles. And now we seem to have near full control of the tentacle. A couple observations. The cable attached to the most proximal, that's closest to the base link, is certainly holding the most load. That's because it's holding up all of the weight of the links that are more distal, i.e. farther from the base, from its attachment point. I previously thought that the tentacle would need many more cables attached throughout, but we can even actuate these cables independently, 2 degrees of freedom, in a single bend direction, which is great for making more complex shapes than just a single bend. Don't forget, however, that this tentacle is not supporting any kind of load at its end effector. We are struggling to simply get the tentacle to move on its own, which in robot design probably means your robot is a piece of crap. Don't forget that the stiffness is primarily there to counter the effects of gravity, which can also be done by decreasing the mass of the tentacle and having less stiffness. In the end, it's the ratio between the stiffness and the mass that determines how controllable the robot is. Both increasing stiffness and decreasing mass help increase accuracy, but decreasing both stiffness and mass help decrease effort. So you're better off making a tentacle as light as possible. So I'll tell you what you're not going to be doing with these arms. You're not going to be climbing walls, you're not going to be lifting cars, and you're not going to be fighting spider people. The applications this sort of arm seems destined for are actually much more benign, and in my opinion, more valuable. While a standard 7 degree of freedom arm has a great use in many applications, it is extremely dangerous. A position-controlled one of these bad boys will go right through you if it's asked to. As such, they are not meant to interact with humans. A lightweight compliant tentacle like the one I've studied in this video is far better suited for assisting humans with delicate and lightweight if not super precise, tasks. These could be household robots, assisting with cooking or bathing for those who can't do it themselves. They could also be laboratory assistants, which ironically is what their Marvel Universe counterparts were meant for in the first place. I'd go as far as to say they could never be used for anything violent. And that is why I'm so happy to be working on it. Man, I love this kind of investigatory engineering. It reveals so much about how things work. There's still so much more to talk about here, especially about how this type of tentacle in 3D actually becomes overactuated once the aforementioned problems get solved, meaning its design flaws become more apparent. I've tried solving this by introducing another degree of freedom to each joint, axial extension. But wouldn't you know it, that completely ruins the controllability of the arm, while showcasing a pretty cool stretching tentacle, which is something I've only seen in the movies, even if it is a lot slower and a lot smaller. I'm still not convinced that a tentacle even remotely like this is the best solution. For instance, you may have a much easier time with a pneumatic or air-powered tentacle, but I haven't looked enough into this to know for sure. While the actuation and controllability of the tentacle may be easier, there could be other shortcomings like load or speed limitations. In 2020, I posted a couple videos that chronicle my first tentacle build, which was designed and manufactured in just 1 week. Hey, it was quarantine, I was super bored. You can check that tentacle out. It was much stiffer than what I've shown in this video, but it was probably more controllable. I only needed 6 muscles to actuate the entire thing, with 2 degrees of freedom per bend angle, leading to a whopping 4 degrees of freedom arm, with 2 halves of the tentacle each bending in both yaw and pitch. Thus, 6 actuators and 4 degrees of freedom means an overactuated system. Plus, the tension in these cables is so high you can see it warping the base. There's all sorts of give and take when designing complex mechanical systems like this, but it's up to me at Dragline Dynamics to find the best solutions, which I have done using actual science for web shooters, 3D printing, and more. Please support Dragline Dynamics by donating to me on Patreon, where patrons contributing $5 or more per month will be able to download all of the tentacle 3D printing files I've presented in this video. Just a note, you gotta print the flexible joints in NinjaFlex Cheetah or an equivalent material. You can also buy a nice hoodie or a nice mug on my Spreadshirt shop, which you can access through my YouTube channel in the store tab. The links to both my Patreon and my merch, as well as my Discord server, are in the description below. Leave some likes and comments, and especially questions and challenges to my claims. This is the type of educational material that greatly benefits from that kind of dialogue, so let's keep it going. If I get enough engagement for this video, a follow-up on robotic tentacle development will be posted sooner rather than later. Don't forget to follow me on Instagram for more frequent updates. Stay safe, stay amazing, and I'll see you guys in the next one.